Hello everyone, welcome to my video. My name is Dr. Satyanarayan Rao, and in this video I'm going to talk about how the Fourier series was developed for the periodic signals in the 1820s by the Fourier, and then we will see how the Fourier transform extended it to non-periodic signals as well. And then we will see how discrete Fourier transform, what is the difference between Fourier transform and Fourier series, and what is discrete Fourier transform actually, which made possible that we can apply Fourier transform for digital signals. And we will also see how we can solve such problems in SciPy. And I hope by the end of this video we will have a clear picture on how each versions of Fourier transform has its own purpose and how it is solved, and how we can use SciPy to implement some of these algorithms. And we will discuss a little bit of historical context before we compute Fourier transform using SciPy Python library and understand what it means to have Fourier transform, and we will do certain exercises in SciPy. As a historical context, it was in the early 1800s when there was industrial revolution across Europe, and understanding heat flow was very important because there was this steam engines that was powering the industrial revolution, and steam engines had parts like heat cylinders that was periodically introduced to heat and then was allowed to cool, for example like pistons and other mechanical parts. And so engineers needed to understand how metal would behave under these repeated thermal stresses. And also this was the time when there was a lot of buildings like roads, constructions of roads and buildings, and so there was interest in understanding how periodic heating from the sun would affect these mechanical structures. And also many of the industrial processes involved repeated heating and cooling of materials, like for example metal forging or glass making. All this understanding heat flow was crucial for all these processes. And before Fourier, there was no formal heat equation. Heat flow was understood as only qualitatively. We knew that heat would move from hot to cold regions, and different materials would conduct heat differently, except that there was no mathematically way to represent the heat flow. And Fourier was the first person to actually write down something that actually explains how heat flows, which is now known as the heat equation. And why heat equation was important is that it was the first partial differential equation to describe a physical process. We now have a lot of physical processes that are often described by partial differential equation, and this was the first partial differential equation that was given by Fourier that described how the rate of change of temperature is proportional to the difference in temperature between nearby points. So once Fourier wrote down his first partial differential equation, the heat flow equation, he was interested in finding what kind of solutions that would satisfy this equation. He was particularly interested in heat flow in a rod with periodic heating in one end and cooling in the other end. So Fourier realized that to solve this heat problem, the solution needed to handle the periodic input, like heating one end at periodically, or like daily heating from the sun. He needed a new mathematical approach. He found out that any periodic patterns could be broken down into simple waves, and these waves could be sines and cosines of different frequency. Like if we have any periodic patterns, he proposed that we could break down them into different sines and cosines of different frequencies. This led to the conclusion that all periodic patterns, whether it is heart, ECG from a heart or anything, could be represented as sine waves. We could build any periodic functions by adding up sine waves, like it is the Lego block. For example, even if we have a square wave like switching on the light continuously on off, it's like a square wave, but Fourier showed that it could be constructed, even the square wave can be constructed by having infinite sine waves together of different frequencies, even though they had sharp corners in the square wave. So, although heat equation has nothing to do with the periodic functions, this was the same equation that led Fourier to describe how all periodic functions behave and discover the underlying mathematical truth that any periodic function can be represented in a way that we will see in the Fourier series. And the original Fourier series was designed for periodic functions, but as field of analysis evolved, the concept was extended to non-periodic functions. This led to the development of Fourier transform. We will also talk about the Cooley-Tukey algorithm that was found in the 1965 and it's implemented in SciPy. We will also discuss about discrete Fourier transform, and we will also do some exercises in SciPy using the Fourier transform. So to understand the Fourier series and Fourier transform, we start with the concept of periodic signal, which is a signal that repeats itself after a fixed duration t. For example, here it can be like a sine wave, or it can be like a square wave, and it repeats itself. And it's defined as x of t plus t is x of t. And Fourier series actually allows us to express any periodic signal as a sum of complex exponentials. Or here it's the sinusoids. If we consider the Euler's identity, we know that it's e power I theta is cos theta plus I sine theta. So the summation of exponentials here, complex exponential here, is nothing but sines and cosines. And here the Cn's or the Fourier coefficients, which tells us that it is capturing the amplitude and phase of each of the frequency components that make up our time domain signals. And when we extend the concept of Fourier series to non-periodic signals, we get the Fourier transform. Here x of t can be any general signal which need not be periodic, and it can be represented as a summation or integral of infinite complex exponentials or infinite sinusoidals, and we get this is known as the Fourier transform. And here x of f is the frequency domain representation of our original time domain signal, which can be both periodic or non-periodic, and so it's capturing the frequency content of all possible frequencies f. However, in reality we don't have a continuous time signals or a continuous frequency domain. For instance, we can only measure physical signals at certain intervals. For example, whether it is heartbeat or any events, we can only measure as a discrete sampled version of the reality. For example, in reality the signals look more like here, like digital signals, where we can only have sampled versions. And so for digital signals, the Fourier transform is called as the discrete time Fourier transform. Here the x of n are our digital signals, and it can be represented as a summation of complex sinusoidals, and we get a continuous frequency response. Here omega is the continuous frequency response of our digital signal. In essence, DTFT gives us a way to understand frequency response of a digital signal, but it produces again the omega. Since omega is continuous, we have infinite continuous frequency spectrum. Though this is useful for theoretical applications, it's not practical for computations, since we cannot have infinite number of signals on our computer. And so this is where we have discrete Fourier transform, where we have the k, which is the digital or sampled version of the frequency. So when we sample DTFT into the digital frequencies, we get discrete Fourier transform. So we have both x of n and x of k as finite, And this is where the practical application of Fourier transform comes. So in practical terms, the discrete Fourier transform allows us to compute frequency response of finite length signal where x of n is of finite length, and it gives us a discrete set of frequency component, each representing the strength of particular frequencies in the signal. And so if we apply DTFT to this signal, we will have some kind of discrete frequency response on our k-axis here. And if we apply a DFT, we would have something like a continuous frequency spectrum, which represents here, but here this will give me a discrete frequency components. So as a summary, the DFT is a practical computable version of the DTFT. It analyzes a finite length signal, making it suitable for digital systems. And it's widely used in digital signal processing applications. And DTFT is just a theoretical tool that will give us continuous frequency response of any discrete time signals or sampled version of continuous time signals. So now having understood like different types of Fourier transform and the most practical discrete Fourier transform, we will discuss about one of the breakthroughs in the fast Fourier transform, which was the Cooley-Tukey algorithm by two computer scientists known as John Tukey and James Cooley. Now before the Cooley-Tukey algorithm, if we had n point in the signal, the Fourier transform computation required n square operation. So it scaled as n square operations. And what a Cooley-Tukey algorithm did was they introduced a clever technique of divide and conquer, actually, which splits the original problem into smaller parts. So instead of computing DFT, what Cooley and Tukey did was they split our signal into even indexed signal and odd indexed signal. And so our signal was represented as even and odd signal. In that way, we could compute two smaller DFTs as compared to a larger signal. So this smaller DFTs was of the order of n by 2. And so by doing by splitting the signal into even and odd indexed signal, it could be shown that the order of operation is something like n log n instead of n square here. And so for example, if we have 1000 point DFT, it becomes like 10x times faster when we compute n log n as compared to n square. And so this is known as the fast Fourier transform, and these are the two scientists who invented this algorithm that gave rise to computing discrete Fourier transform in a much more efficient way. And now in the next few sections we will see how we can compute Fourier transform using the scientific computing library in Python known as SciPy. So as a part of SciPy exercise, what we will do in this simple code is to generate two signals. So first we will generate two simple signals which are sinusoidal waveforms of frequency f1 and f2, and what we will do is we will combine these two signals. We will do a superposition of these two signals to get a mixed frequency signal. So we will just add up these two signals, and then what we will do is we will compute the fast Fourier transform of our mixed signal, and that should show us two peaks because we mixed the signal with two different frequencies. And then we will implement a low pass filter, which means we will remove the higher frequency components from our frequency response and then try to reconstruct back our original signal, which should contain only the first signal without the signal 2, because it should be supposed to be removed by our low pass filter. So it's the implementation of frequency selective filtering. We will see after we compute the inverse Fourier transform whether we get back our reconstructed signal. So here is the code that I will also share in the description, and so I will briefly explain what this code does. So here we actually import the necessary Fourier transform libraries from SciPy, SciPy.fft, and IFFT is the inverse Fourier transform, and for scaling application we need FFT.frequency. And you can have all this information by just reading its documentation. SciPy has a good documentation, and I'm using some default plotting style. And here if you come, we are defining the number of points in our signal, and we are defining the time array, and we are defining two frequencies for our signals. One is 50 Hz and one is 120 Hz, and these are our two signals, which are simple sinusoid of F1 and F2. And the mixed signal is now the sum of these two signals, and we are computing here the FFT of our mixed signals. Finally, we create a low pass filter here with a cutoff frequency of 100, which means it should remove the signal 2 when we compute the inverse Fourier transform after applying the low pass filter. And so we are plotting our two signals in the first plot and also the mixed signal, and here we plot the frequency response of our mixed signal. It should show us the two peaks. And finally we are plotting the frequency response of a low pass filter. That should be 0 after the cutoff frequency and 1 within the pass band. And here we plot the inverse Fourier transform of our low pass filtered signal. And let's see what we get when we run this code. So in our first panel we see our initial signals. The green line shows the 50 Hz signal, and the red is the 120 Hz signal. And the blue line shows you the mixed signal, which is the sum of the two signals. And you can notice that how mixed signal combines feature of both 50 Hz and 120 Hz. And in the panel 2, we show the frequency domain representation of our mixed signal. So the blue curve, the frequency response of this blue curve is here. And it shows two peaks at 50 Hz and 120 Hz, which means we now know what are the components we have in our mixed signals. And now what we are doing in the third panel is we are applying a filter response like this, which cuts off at 100, and so it will remove the 120 Hz signal, and it will only pass the 50 Hz signal. Anything above 100 should be cut off. And then here what we are plotting is we are computing the inverse Fourier transform of this peak without the 120 Hz, or we apply the third panel frequency low pass filter into the second panel and then compute the inverse Fourier transform. And here you see the green signal is the filtered signal that we get from the inverse Fourier transform, and the black dashed line is our original 50 Hz signal that is in the first panel. So you see it matches. So by converting signals into frequency domain, we can manipulate them with filters and then we can convert back. So we have a powerful tool here for signal analysis and processing. So as we come to the end of this video, the applications of Fourier transform actually extends beyond the simple signals that we showed here. It can be like audio files or images, or even vast arrays of possibilities in data analysis. Again, thank you for joining me in this exploration of Fourier transforms. If you found this useful, consider exploring more and experimenting with these techniques. And I will leave this code in the description below. And please do consider subscribing and comment if you have any questions about these techniques. We will soon meet with another video of similar nature. Keep learning and remember to enjoy life. Thank you again.